the biases that we train into these models are very difficult for us to recognize.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Dave Finch. Today I'm joined in the lobby by Jason Kridner, co-founder, community manager, and self-described chief cat herder at BeagleBoard.org to discuss open source machine learning systems for embedded applications. When Jason Kridner and his colleagues founded BeagleBoard.org, their mission was to create powerful, open embedded devices and a global collaborative community of users. Back then, the notion of practical, enterprise-grade machine learning on ultra-low-cost, open-source embedded devices seemed out of reach, if not far-fetched. But in the last few years, Jason has become witness to the promise of machines learning to learn using technology that he personally has brought to life.
So started up BeagleBoard.org really to try to give more people access to the tools for developing at the time really ARM processors. We were just getting to the point where ARM processors were able to run desktop operating systems and so much more. And now we've created the BeagleBoard.org Foundation focused on educating people around the design and use of open source software and hardware to give people more access to learn the guts of what goes into single board computers running open source, namely Linux, right? But not just focused on Linux, right? So really to make those more accessible, to teach people how to actually build hardware, electronics, circuits, and make sure that there aren't barriers for them getting access to that. So part of that's making it more affordable, but a big part of it is making it open source. Sure. And one of the things that kind of makes BeagleBoard computers different. There's no kind of restrictions, and because it's open source, people can actually go and get the designs and customize them, and build their custom things in any quantities. We make sure that the components used are available through distribution in quantity one, so people can make custom designs. Mm-hmm. So being all open source hardware, but also having them designed to do controlling things, right? So processors that are optimized for industrial usage. And so they have things like these PRUs that are ultra low latency microcontrollers. And you'll see other like acceleration components like DSPs, embedded vision engines and things to try to reduce the latency to do very targeted processing.
Tell me about where we are right now with availability of highly viable machine learning, we'll say either technologies or solutions or some really cool things that you've seen where you say, yep, we're definitely getting traction in the open source arena on this.
There are wonderful tools out there for open source machine learning development. The tool environment is remarkable, especially when you look at like what you have for training. It's mind-blowing how far we've come just within the last 5 years. Mm-hmm. I remember taking neural net classes in university, and I'm scared to say how long ago that was.
3 years, right? 4 years?
Right. Yeah. But it all seemed like it was all so theoretical, and you kind of wondered if any of this stuff was ever going to be possible in your lifetime. You could kind of make sense of the theory, but you'd never be able to train these neural nets to actually do anything useful.
Right.
And big data and cloud computing, coupled with these open source tools, have really made it possible. And what you can do in data science today and is just, it's mind blowing. I mean, I don't even know where to start because it's all just so outstanding.
Mm-hmm.
I think that when you start getting into the embedded side, so what can we do in electronics close to the source, right? It's still very limited. The reason for that is because the data that you're dealing with gets to be so specialized so quickly, right? Having huge amounts of image sets or huge amounts of words, or even like spoken words, or even like geographical data, right? So just information about our world and the sensors that are collected on these global scales. You can get massive amounts of information, user preferences. But when you build an embedded system, we can do great at things like voice recognition and kind of limited things. But like we're seeing the embedded world trying to tackle some more things like machine failure, right? There's a whole lot of progress being made in terms of recognizing, early failure conditions, but there's still so many places where there's just not these big data sets to train the models on as there is in like, kind of non-embedded spaces.
So if I'm new to all of this, I'm an embedded engineer. Maybe I've been working in industrial controls my whole life. I've never had to make intelligent, quote unquote, things. Certainly not things that are capable of kind of training themselves or doing their own learning. And I want to get involved. I can go to GitHub and I can find solutions that will get me started with fairly reliable machine learning functionality to place into my system. Is that right? Is there a wide availability at this point of sort of entry point and even expert modules, we'll say, that I could pull off and drop into hardware?
I'd say that, so there's different levels of solution depending on the type of problem that you're trying to solve.
Okay.
I'd say that, if you're trying to do, some examples to see like some object recognition, segmentation types of applications, there are some pre-trained models that you can get and just run on like video streams in order to see some classification and segmentation. And then there's ways that you can retrain the models, like teach it something new to see, right, to recognize and to classify. So that's not too involved. I'd say ultimately that stuff kind of lives just as a little bit of an example space and not so much what you might want to actually put into an embedded system. So we're working with a couple different universities to try to gather some more interesting data sets, but you're probably going to want to train a much simpler model than what you're actually going to see these examples of. Now, if what you're trying to do is like, I don't know, like, are you trying to recognize defects on a manufacturing floors? You're running things, across a conveyor line. I won't say it's easy. Today, I think, is the time to play, and there's some really amazing things. And there are some real deployable applications, but most of the things that you're going to be building in real systems are going to require a high degree of expertise today.
I should think so. I mean, yeah, you can go on TensorFlow or whatever and find those beginner models, but
absolutely, and that's kind of the way that we would take some of these pre-trained models and do things with TensorFlow, and then transition those into acceleration if what you need is more performance. That's the development path today.
Now, fully open source ecosystems have to include open source hardware, of course, which also means hardware components that are available in the mass market. You have to be able to buy the chips. So let's look at the microcontroller. BeagleBone single board computers use the Sitara mixed processor controllers from TI. They're pretty beefy. ARM Cortex-A, integrated DSPs, right? Coprocessors. Is this bringing to bear more horsepower than might be needed for, say, a majority of embedded machine learning applications?
You can start doing machine learning network execution in something as small as like a Cortex-M class of processor.
Okay.
There are things like TinyML, and like you can have, you don't have to necessarily be processing huge 2D data sets, right? So, voice, right, is a good example of that you can be processing with a much smaller sample, right? So that you're dealing with rather than video images. Training is going to require a somewhat bigger machine, right? A lot more resources to go and do the training of the model. But once you've got your weights, executing the neural net doesn't necessarily have to be even something as powerful as a BeagleBone AI. I mean, that's it's actually a reasonably powerful engine compared to what you
Sure.
need for kind of getting intro into machine learning.
Yeah. I haven't trained anything. Well, I have successfully, with the help of my wife, trained our dog to hit a button when he wants food.
That's you trained a neural net. Not quite the same thing. A little more advanced, I think.
I nailed it. I think
the dog. I mean,
yeah. The dog has like maybe 4 nodes. We're not even talking like 128 at this point. But he nailed it. It took him 6 months. But to what extent do the existing tools that we have? You mentioned once we get into the embedded side, to what extent do these tools require knowledge of neural networks, training, tuning the systems, that sort of thing?
Yeah, so there's a lot of kind of existing models and existing data sets that you can just leverage and get a lot of mileage out of, depending on the types of problems you're trying to solve. The problem is the coming up with the topologies and the data sets for new problems is still very difficult. Now, there are some models that work in very seemingly general cases. So it's not that you necessarily have to go there, but trying to really understand what's going on is really difficult. Like we can't even really figure out how it's working, right? We know theoretically how it's working, but like the biases that we train into these models are very difficult for us to recognize, right? I mean, like the things that make you uneasy sleeping at night, right? I mean, it's just...
Yes, exactly. I've read about many instances where a bias, however unintentional it may be, was coded into, for example, facial recognition programs. You might see 1 or 2% error rates in recognizing white men versus, upwards of 30% or even higher error rates recognizing women and people of color. That's a problem.
It doesn't even have to be intentional, right? I mean, if anything, these neural networks are inclined to have even greater bias, right? It's just like just because they're going to encode whatever bias exists, and they will follow false correlations, right? So
that's right. That's right.
If there's a correlation, whether or not that's causal relationship or not, they're going to just encode those, and then people feel like they can absolve themselves of that bias, right? Because it's just what the machine's doing. It's like you trained it to be biased.
Exactly. And these coded biases, they're not necessarily coming out of shoddy little garage operations. These are apparently popping up in AI solutions from companies like Amazon, IBM, the biggest names out there. And that's why, look, speaking of bias, okay, personally, I just don't trust public corporations to care about social issues or people. There's simply no reason to, especially when you look at the ridiculous people who run these things. And this is why I think open source, readily available technology is so vitally important, because engineers can and will solve enormous problems if they simply have access to tools and an open exchange of knowledge.
Yeah, at least you have the opportunity to peel apart the layers and do some analysis, right? Some of the, like, if you look at the trained models to try to do the analysis of what its built-in biases are and like how it's ultimately making decisions, that analysis is very difficult.
Sure.
But at least you can do some analysis of the solutions you're building up and be engaged with the community that's creating those solutions. So I think that's a real value that we add. I hate to be the perpetually optimistic purveyor of technology. I don't want to do that. I want to build technology with a purpose, right? But it is somewhat the case that if we don't build it, someone else will.
Right.
And if we can build it in a way that it's open for peer review and analysis and criticism, taking a fair bit in terms of like security, right? Because we've opted towards making things open and hackable, and at the same time, like, so you don't necessarily lock it off from like dictionary passwords for root logins, for example. And those sort of criticisms are constructive, right? How can we make security better? And at the same time, how can we make neural net models better? Mm-hmm. Especially when this stuff could be controlling, or involved in the control or feedback of very significant objects, right? So we look at how, where would I use machine learning with a BeagleBone AI, right? So we're seeing some of the earliest applications for that in things like wellhead monitoring, either in drilling or in extraction, where somebody is going to encode some human learning about vibrations that are happening in the system and response. Like when you're drilling, if you hit different materials, like an experienced driller can actually kind of figure out when they're hitting something that's different, potentially dangerous, and notify. So it's trying to encode some of that human knowledge. That's ultra valuable. So we want to try to see that happen in as responsible ways as we can.
Hey everybody, it's Dave. This episode of Moore's Lobby is sponsored by Allied Electronics and Automation, a high service level authorized distributor of industrial automation, interconnect, cabling, and electromechanical products. They carry more automation and control brand names than any other distributor in North America, with a broad range of product solutions from more than 500 brand name suppliers, including BeagleBoard. With over 3.5 million parts available and more than 170,000 SKUs ready to ship, Allied's global footprint and world-class logistics allow them to give customers the products they need when they need them. Connect with them today at www.alliedelec.com or call 1-800-433-5700. That's 1-800-433-5700, alliedelec.com. All right, back to the show. Welcome back to the lobby. Jason Kridner's passion for building computers and embedded systems began in elementary school, when his mom quite sensibly would not allow him to open up the family computer and play with the electronics inside. He took matters into his own hands, building timer circuits from Radio Shack and saving his money for Z80 processors. In an open letter to his BeagleBoard community, Kridner notes that, quote, "I've always wanted to see those same freedoms to learn about computers and electronics imparted on the next generation, as well as short-circuiting the connection between computers and electronics." Today, BeagleBoard.org offers about a dozen single-board computers, from the original enthusiast BeagleBoard to the ultra-powerful BeagleBoard X15 computer and the enterprise-grade BeagleBone family. BeagleBone AI was developed specifically for embedded AI and machine learning applications.
The highest end is still BeagleBoard X15, but we took that same processor and kind of made something a little closer to BeagleBone Black, right? So it follows the basic BeagleBone Black form factor. We moved the power connector. Now you get the Type-C for the power. So we get power and the USB over that same connector. So you can actually fit these inside the BeagleBone Black enclosures. And you can connect up the capes, right? So all the add-on boards that you'd have for BeagleBone Black, you can now work with the BeagleBone AI, but yet you've got this beast of a processor in there.
Yeah, and the idea being, okay, so beast of a processor, you mentioned earlier that there's running the trained AI program, and then there's training the algorithm. Two different animals from a processor standpoint. Is the BeagleBone AI capable of doing that training, that heavy lifting?
It is. I mean, if what you're trying to do is training for the smaller microcontroller type of platforms, then it's great for that. If what you want to do is train these heavy duty image recognition type of models, I would not recommend it. I would highly recommend you do those in the cloud. You can do some incremental learning. It's very suitable for doing some incremental learning. But it is more of it's the inference engine side of things that gets accelerated, not the training.
Gotcha. The exciting thing is then you've got this very powerful engine. And like you said, one of the other beautiful things about the BeagleBoard ecosystem is that you've got these capes that already exist. Other designers, have developed widely available capes, but you could also design your own cape just to plop down on the header that supports it. And that's where enterprises and startups and individuals can really leverage the very powerful computer that's set up for this. Also, the wide availability, we'll say, of source code, proven code, proven architectures, and proven models, and develop the special hardware that sits on top of this engine for their specific application.
Completely. Yeah. So there's hundreds of cape examples out there, because a lot of times these things are built to kind of solve one-off problems. You'll see some come available and then maybe not be available from the ecosystem. And to that end, we've developed our own line of capes to try to solve a number of different problems. And that's something that we're also continuing to evolve, that ecosystem, having things like relays and loads and CAN bus so that you can get something to perform a lot of automation tasks, right? Because that's something we see a lot of, is people just using these in automation systems. And the robotics cape is a nice one that allows it kind of integrates a lot of the features that you'd see in something like the BeagleBone Blue.
I was going to ask you about robotics, because in so many ways that is going to be going hand in hand with machine learning.
Absolutely. Beagles are heavily used in a lot of robotics applications in mechatronics for universities, but another common university usage is teaching advanced manufacturing. And that's those capes are such a fundamental part of doing that, right? Where you need to get the right interface to do that control. And so you've got a lot of the PRU pins, you've got analog pins, a lot of signals to work with for building out an embedded system, right? That's the point.
Yep.
A lot of the power you get to see in some of these custom Linux distros or applications kind of built around it. Things like Machine Kit, where people build all of these CNC, like the Pocket NC, that's a 5-axis CNC mill, or people have done pick and place machines, and so all these just industrial equipment, but also more hobbyist things like the RG Pilot project, right? That came out of our so it was ported to Linux as a partnership between BeagleBoard, the Google Summer of Code, and 3D Robotics. Mm-hmm. Was a port of RG Pilot onto Linux. So it uses the PRU microcontrollers to do kind of the radio front-end processing, so it can receive the radio control signals, and then it uses the PRUs also to generate the PWM that tells the motors how fast to turn. So that's also done through these little microcontrollers, and then running real-time Linux kernel. You just go get these whole setups there, and there's different distros for lighting controls and all these kind of little cottage industries and DIY things that kind of spawn different technologies that are really fun to play with.
Absolutely. I actually want to dive into the PRUs first, just a second. My first entry into this was the BeagleBone Black. And the person who introduced me to the concept of the programmable real-time unit, these PRUs, was one of your board members, Drew Fustini. Because I was asking him, well, what makes this cool versus maybe that single board computer or some of these other proprietary things? Like, I think at the time, Freescale was coming out with some enormous IoT board, But at the time, it wasn't blatantly obvious in the documentation. But he said, check it out. This thing, you've got access to these programmable real-time units. So if you do need to be doing advanced motor control or, like you said, PWM control for, intelligent power supplies, like in a server application. So is this something that's kind of unique in that Citara processor?
It very much so. And it's very unique to the Citara processor, but also we just got a GCC support for the PRUs. So one of the community members pushed that through. So we'll have a fully open tool chain for working with the PRUs. I hope the statute of limitations is passed on this, but the whole, the way the documentation got released for the PRUs, there was a chapter in the technical reference manual, early editions, that included the documentation on the PRUs. And TI stripped it out.
Oh, yeah.
So they actually removed it because they said this stuff is going to be too hard for people to program. The people that are actually going to use this, we're going to release some protocol support for supporting different like Ethernet, real-time Ethernet protocols, right? And use these PRUs to provide that solution, right? It was a solution to a given problem. It just happened to be a really generic solution. So they took the PRUs and put them in there for that purpose, but then took them out of the documentation. And I begged and pleaded, and eventually, got those documents and released them through the BeagleBoard GitHub pages, right? So we actually created a GitHub project and released the same documentation and just absolved TI of any support of these initially. And people forget how like ingenuitive the community is, right? Because the community is often they're people who are engineers. Well, not all of them, right? There's a lot of hobbyists that have no engineering background at all. But even those, they're able to go and solve problems if they know why. So my motto is just to find ways to get out of the way. And if you can get them enough information to just let them figure out why they'd even want to go bother, they'll figure it out. And that just so happened.
Yeah. And then it was like cat's out. You can't put the toothpaste back in the tube.
No. And now if you go pull the technical reference manual, the chapters are all back in the manual now, right? So it's like, it's too valuable, right? And but there was time to kind of get a lot of information out there about what you can do with them and examples to kind of show what their value is that are all coming out of the community before TI ever put the documentation back in the official documents.
Okay, so for our listeners who aren't familiar with Beagles, what is the value in having access to a PRU on your single board computer or in your embedded design?
The trying to describe why they're so valuable is a little tricky. The register map, actually, like if you've ever seen CPU architecture, RISC CPU architecture, like you'll see have these register files. Mm-hmm. And so R30 and R31, those are like the names for the general purpose register files where every instruction could just do the add, multiply, subtract to them, whatever. Mm-hmm. So R30 and R31 are actually directly mapped to IO pins. Aha. So that's kind of the magic. You could actually do a zero overhead loop and do an XOR on pins and like create an inverter that would run, at 100 megahertz, right? Well, why is that super, super valuable, right? The guys at MIT, the Center for Bits and Atoms, I think have kind of been able to kind of wrap their heads around this a little bit, mm-hmm. To try to describe it to people. And I don't know if I can do it justice, but right. They created a little bit of a benchmark on like the things that you need to be able to do to actually go make machines that make other machines. And that control loop feedback is a fundamental part of that, right? You actually have programmatic cycles between the input of pins and doing some work and then output of pins, right? Because that's what a control loop is, and that's what you want to do if you want to make a machine that's going to make other machines or make other things. And so they had a benchmark of like for what dollars you can get like what level of performance. And if you just throw the lowest cost Beagle out there, the Pocket Beagle, it totally blows their whole chart away, right? It's more than 10 times faster than anything else that's out there.
Right. And I have a Pocket Beagle, by the way. If people don't know what that is, it's about the size of my big toe. I mean, it's such a small computer. It's amazing.
Yeah. It's not the credit card size computer anymore. Now it's like 3 of them per credit card.
Right, exactly. It's insane.
Yeah, it's those sort of applications where you're wanting to control a machine, but you're going to need a lot of processing power to kind of take the high level information about what you're going to want to do mm-hmm. and crunch it really fast so that the high throughput side. And then there's that low latency side of actually making the motors move and making sure, dealing with the feedback so that they actually moved there and responding to that. So that combination of high throughput and low latency is pretty unique in what the Beagles can do.
One of the cool things about BeagleBoard.org is that it has been contributing to the transformation of our industry, not as some rogue outside organization, but instead from within the industry itself. Your background is in, I mean, you're a double E, and you worked at TI for a while.
Just 28 years, not too long.
You've had a brief history, a little stint. And your background was it embedded computing mostly, or did you do analog stuff?
My history, I came into TI as a product engineer. I guess I always, like in school, I was always super interested in embedded systems and signal processing. I specialized in analog in school with some signal processing. But when I came into TI, I started out in product engineering, doing things like latch up analysis and data sheets and characterizations, and then I moved quickly into applications, mostly audio. I did ASIC design, so interface circuitry and ASIC design, board level design, and then as well, and then kind of transitioned into more of framework software, lot of integration software side of things.
Okay.
I've always kind of switched a little bit back and forth between hardware and software. I'm one of those people that started programming when I was 8.
Nice.
And and I always kind of wish people would actually get computer science degrees before doing programming. Looking at engineers' code.
Yes, I know where you're going with this. I want to hear you say
it. You probably already got me to back off of it too much, but it's not beautiful. Engineers code to get the behavior that they want to see on the other end, not necessarily with the mindset of how do I make this modular and maintainable and like draw the right contract in between the different functions. So like one of the easiest things for me to say is, guys, just use Linux, because at least, there's an enforcement level of some sort, when you push it into the Linux kernel, even though in some respects it's kind of spaghetti, but at least it's like really peer reviewed and really structured. And so I came from a personal background in software, but went to engineering and doing programming with engineers. And mostly in audio. Also did a stint in modems.
Nice.
I loved the audio stuff, and I loved the DSP. I think that was some of my favorites. But as we were, kind of saw the cell phone industry changing, and really saw that as an opportunity to try to give back a little bit, right? And help the next generation, on board, and even just allow more peers just to have more control over the technology that's getting created and which direction it's headed.
All right, I want to thank Jason Kridner, the man himself, for making time to chat with me today. Be sure to subscribe to Moore's Lobby on any of the major podcast platforms, including Apple, Spotify, and Google Podcasts, to enjoy new episodes every 2 weeks with industry experts from world-renowned companies who join us to chat about leading-edge technology and engineering topics. You can also follow us and catch prior episodes on allaboutscircuits.com. Thanks for listening.